Let me continue our discussion of routing algorithms, and I will talk about the distance vector algorithm. So one of the key differences is in the distance vector protocol compared to link state is the fact that you don't have to know the whole topology. And the only thing that you need to know is your neighbors. So you need to know that you can reach the neighbors and some specific costs associated with the neighbors, and anything neighbor willing to tell you. For example, if a neighbor can also know about its neighbors and is willing to tell you about its neighbors, then that would be enough for the purpose of this algorithm. And the whole idea is that the whole process is some kind of iterative process, and eventually, so you got your knowledge, you shared your knowledge that you connected to neighbors, neighbors shared the knowledge with you that they connected to their neighbors. And eventually you kind of aggregate information that you obtained from the neighbors aggregating information that they obtained from you and other neighbors, and eventually they build up kind of information in their own routing tables, or in their own tables. The steps in the distance vector protocol are much simpler than the steps in the Dijkstra algorithm, but it's a little bit more complex to describe and maybe a little bit complex to grasp because of the iterativeness nature of the algorithms, because you depend on something that others tell you, and that's it. Let us define this terminology, which is a little bit similar to what we had before. So we also had a dy before, but this one is dxy. And the reason here we have this dxy is because it's not our cost, but rather it's a cost of our neighbor to reach y. So for example, if A is ourselves, we're going to be considering a db some node after the b, and we're going to considering to some other node outside. So kind of from the perspective of node B, distance to someone is x, and from perspective of node D, distance to reach someone else will be something like y, for example. And what the basic step of the algorithm is simply get the information from its neighbor about dxy. So that's we want to collect this information. Initially, we only know, we basically know nothing about neighbors and only know the cost to reach the neighbor. So that's kind of initial information, and this is the same notation as we saw before, like CXV. And then after the neighbor tell us what they can reach, we obtain some information, and in a simplest case, I'm gonna tell B my reachability to D, and I will tell B my reachability to D. Yeah. So basically, from the perspective of D, eventually I will receive what I'm gonna receive D A B will be 2, and D A dA to reach D will be 1, and this information will be so this one will be shared with D, this will be shared with B, or in principle both of this can be shared with both guys. It's just not too useful to B to know that it can be to reach B through A, because it's basically the same path, and vice versa. Okay, so we got this part of information. And basically the step of the algorithm, or like the iteration of the algorithm, is quite simple. What you need to do is simply get to evaluate all the paths that you have, like all the vectors that exist, and simply try to figure out whether you can reach through any of this path plus the cost is cheaper than reaching through some other means that you already know about. So what you're looking at is you're looking at kind of this weight, you're looking at this weight, you're looking at this edge, and just considering every available information that you have. You may get over kind of as many iterations will go, you will get more information and more information about the hosts that are not directly reachable by either B, C, or D, for example, like if we have more hosts available. But in the simplest case, in this case, it just is quite simple. And as you can see on this example here, I'll just reset this. So what evaluation here is, like, we trying to evaluate how to reach f simply by calculating if we can reach it, like looking at the AB link and checking whether we can reach f through b more effectively. So like some kind of a notion of how to reach f through this point. Then we're looking at the kind of D connection, so this path, and some understanding of how to reach f through D if we have that information. And finally, we're also looking at the C and the same information how to reach f. And basically, we'll try to pick the smallest number if we already know the smallest number, we pick them. If next time, kind of at the next iteration, some of this weight change, we'll try to reevaluate and basically try to pick yet another number. So that's basically it. It can be quite simple, simple logic. Kind of in reality, is just a little bit tedious to show, a little bit tedious to do the calculations. But let us try to actually run the example. So let us just again basically consider the same network of node A, B, node C, and node F. Let me just pick this kind of just 4 nodes, because that would be already a little bit complex, and we'll assign, for simplicity, I'll just put everything here once, and here 2, and here 3, just for the random example. And the point is, the process is iterative, and we have to process kind of each step. We have to consider perspectives of all 4 nodes. So, for example, we have to consider from perspective of A, so it has to be some kind of corner for A. We have to consider perspective for B. We have to consider perspective from B and oopsie. So this one should be C, and some kind of perspective of F. And for some reason, I'm skipping D in this picture. So what we know initially. So initially, we know that A can reach B with 1 hop, because somehow this is we can discover our neighbors. So that's assumption in distance vector protocol. And what we can write is we can reach B through 1 and through B directly. So let's say this way. And the same thing we can write, we can reach C through 1, again, directly. That would be iteration of 1. I put this this way. From perspective of B, I'll just try to quickly write A 1A, F 2F, and that would be iteration 1. From C, what we're going to have, again, iteration 1, A 1A, and F 3F. That is. And for the fun of it, actually, I'll add the additional link and say, let's say it's also 2. Then we need to modify this picture a little, very tiny bit. So what we're going to have, we have to modify B and C. So in perspective of B, we have now C. We can reach this 2 directly, and B 2 directly. Okay, and F, okay, we also have F, B 2, B, and we have C 3, C. Okay, so we've done the first iteration. So you already see there's a lot of writing involved in this process. Again, the process is simple. It's just a lot of writing, a lot of calculations, because we have to consider kind of perspectives of individuals. With the link state protocol, it was a little bit simpler, because we always only considered one node and only calculated the routing basically on a single node. Compared to what we have on this picture, is we know routes on every node in existence. So basically what happens next is each node gives this information to others. What we can do is simply can assume that neighbors will give the step 1 information to their own neighbors. And we simply can try to recalculate what happens at the next stage. So at the next stage was kind of from the perspective of node A, we know information from B and from C. Again, it's quite a bit of calculations, but what new information basically we're going to take is something about F and something about F here, because the rest is kind of A is ourselves, we're going to ignore this part. B we ignore because it's our neighbors. A and C, the same thing. So basically we're going to have information saying from the perspective of B, we can reach F with 2, and from perspective of D, C, we can reach F with a cost of 3. So that's what the information basically we got from the neighbors. And now we simply need to evaluate this information. It's either we need to go through B or through C. And we just simply need to compare and recalculate it. And as based on the previous discussion, what the recalculation is, we're looking at the cost of the going to the neighbor plus cost to reach that destination through that neighbor. So basically cost to B, 1 plus cost of B. So if I say this way, from perspective of A, going to B plus going to, from perspective of B, going to F. So in this case it will be 3, and if I recalculate the same thing, it would be 4. So it will be 1 plus 4. And in this case, it's obviously 3 less than 4. So we pick B as a destination to F. And effectively, what we eventually write, if I kind of figure out how to write this part. So at the iteration 2 at A, this is another part of information here. So we're going to have, again, the same B is 1, sorry, B is 1, B, C, 1, C, and now we have F that we can reach through C through using 3 steps, but we have to go to B. So this is basically the second iteration. Something similar going to happen at different destinations, different hosts, and kind of so on and so on. And I don't know whether we need more iterations, or that would be enough iterations to actually know everything. I think that's it. Yeah, because we only have the kind of 4 nodes, and from the perspective of A, you can actually now send packets to everybody, and that is the smallest cost. In more complex topologies, kind of with the same example kind of shown on the network, there are multiple steps. Like if you have like 6, 10 nodes, you will the whole process will involve multiple steps, multiple exchanges, and you will have to exchange the information, like, or give the information that you recalculated. So for example, the one we just calculated, so from the perspective of A, that you can reach F using 3 steps, you actually have to give this information to both of your neighbors, and maybe this information will be helpful, maybe not going to be helpful. So that's kind of beside the point of the algorithm. You just have to give this information, and then algorithm will try to decide whether it's information useful or not useful. Okay. That's basically the algorithm. There are a few illustrations here and there, but the algorithm itself, as I said, is quite simple. There are several other implications in algorithm, and one of these implications is so-called the count to infinity. So this one is not specifically a problem of the algorithm. So algorithm works, like everything is perfect. If we're given the graph, kind of whatever, with some number of iterations, it will finish. And technically the time complexity overall, it would be similar to link state protocol. So when link state protocol for individual node is n log n, but multiply for different for number of nodes, it would be n squared log n. And something similar you can expect with the distance vector protocol. What's different is a reaction of when something changes. Like this is again not really a conversation about algorithms, but there are some properties in the algorithms that relate to this one. Specifically, if some node disappears, distance vector is actually have a bad reaction. And let's just discuss what is happening on this picture. So initially, before anything bad happened, and like assuming every house, every link has just a cost of 1. What the knowledge that will be disseminated in the network is that C, like D, from the perspective of C to reach D, D, is 1. From the perspective of B, D to reach from the perspective of B to reach D is 2, and that's it. So that's kind of all the information that is necessary. So when link disappears, C may detect this problem and simply remove this information from the further advertisements. But what's not going to happen unless something special is considered is the fact that B still knows that it can reach D with a cost of 2. That's it. Like, it knows this information. It's actually, if nothing special is performed, it can tell that information to C. And if C sees this information, saying, oh, actually, I have alternative path to reach D, and it's through B, because B is telling me that it can reach D with a step of 2. So now, what's going to happen is now C thinks that it can reach D with a cost of 3, because it's 1 plus 2 that was advertised. And that's basically it at this point of time. And it advertises this information to B, and B is looking at this information and saying, I seem like my cost previously was 2, but now it's supposed to be plus 1, because that was my destination I was going to. So now the cost of going to B to D increased to 4, because it's C is telling 3 plus 1 is 4, and it's advertising to C. And now C is saying, something is interesting happening, so B is somehow increasing the path length and increasing to 5. And you probably see where I'm going with this. So this process will technically be infinite. So it will go to 5, 6, 7, 8, and so forth and so on, so on. Like it will never finish, basically. So, and this problem is kind of inherent for this specific algorithm and called the count to infinity, just because something happened and you didn't pay close attention, you didn't tell the other node that you actually were reaching that destination that just disappeared through that node. And kind of something bad happened. So I already highlighted the solution, but one part of the solution is to actually limit this infinity. And as we'll discuss in the routing protocol, this limit to infinity is in the protocol that we're using today in the RIP protocol is 16. So like it's at most there's this 16 back and forth exchanges, after which you declare, oh, actually I cannot reach it, so like let's just stop communicating about this destination, which implies you can only have 16 hops, or actually less than 16 hops in your network. We can solve this problem partially using the so-called split horizon. And with split horizon, it simply means that we don't tell the node that we can reach something with a certain amount of cost if we got this information through that node. So basically, if some information came from C, so for example, C told that perspective of C to D was, let's say, 1, B will not going to be telling any derivative information based on that. So you have to really pay close attention to what internal structures you're keeping. It's not that simple, because you already saw some of the complexities involved. But it is possible to do, and people are doing. And in this cases, when link breaks, this link breaks, C will detect, C will stop announcing that something bad happened, B will not going to be telling that something bad happened, and kind of this count to infinity would not happen. However, there is one additional problem. When this link happens, C detected the problem. And if packet towards D will come to C, the packet will be dropped, or kind of in some way the source will be notified that something bad happened. But from the perspective of B and perspective of A, nothing bad happened, because just C suddenly stopped announcing it, and B and A seem like happy to see that everything is fine, and they still think that they can reach destination D through C, A that knows that it can reach destination B, destination D through B, and everything seems to be fine. But in reality, it's not fine. The packet basically will be sent out kind of waste network resources, but it will never reach the destination because that link is broken. So there's actually additional solution that was added to the process. It's so-called the poison reverse. So instead of just telling, or just stop telling information, you explicitly tell that, oh, now I'm broken. Like the link is broken, like the one that I was advertising to you with a cost of X, now is nothing. Like you better, if you have alternative path, accept me, please use it. But if you don't, then just stop advertising and also do this so-called poison reverse on the way out. So basically, this way it solves the original problem. And if you kind of look a little bit more carefully on these slides with these examples, you also will avoid some of the loops in the system. Okay, so this one I'm sure that was quite intensive. But it's very important to understand that routing algorithm is this fundamental part of networking where we have to some form of automatic calculation of how we're going to reach that destination. Like given all the complexity, like I already show you, we have 80,000 autonomous systems. It's not even individual routers, but rather big systems. And who knows how many individual routers all those systems have. And even simple network, simple in quotes, network as FIU have, I don't know, hundreds of different routers, and kind of network topology is much more complex than the one that I was showing on you on the slide. So this basically highlights we need some form of mathematical apparatus to define how we're going to calculate. And I'm highlighted kind of using these two parts of the same part, that we have a distance vector approach, the one that I just discussed, and we have a link state approach. With distance vector, we don't know the whole topology. The only thing that we know is how to reach neighbors. We kind of basically discover who the direct neighbors are, and we simply waiting for the neighbors to tell us what they can reach. And we kind of in this process, we also tell neighbors that we can reach some destinations. And through the iteration, through the kind of communication back and forth, we eventually can build up the knowledge about the whole network. So that's kind of interesting part of the protocol. Like without knowledge of everything, you know everything that you need to know. And you can start communicating. There are a few problems, like we encountered the count to infinity. We kind of solved it partially with the split horizon, and kind of finally solved with the split horizon and poison reverse. With the link state protocol, it's kind of the process is different because we have to know the whole topology. So some way that would be the business of the routing protocol, to discover the whole topology. And by whole topology, you means I mean every node in a system, like how many different routers in the network, and each link that exists, like available, not available, actively used, not actively used, and some kind of notion of weights for those links. As soon as we get that information, you can immediately recalculate. And to highlight the difference between two protocols, kind of regarding the error processing, if some link fails in the system, link state protocol would not have any kind of count to infinity, because if you exchange the information and all the nodes in the system will discover that that link disappeared, they will simply recalculate, and that's it. That will be end of the story. So reaction to the errors is much simpler in link state protocol, but you still have to discover that something happened. But that would be story for the routing protocols. Okay, so that's it for routing algorithms. That was intensive, but be ready. There will be even more intensive parts with routing protocols.